Hello, Algebra 2. Some of you have noticed that the graphs we've been making of polynomials have really just been rough approximations of what you see when you do the same work on your graphing calculator. And that's true. They are only going to be rough approximations. And I'd promised you that I would talk about how to make them a little bit more detailed, though they won't be as detailed as what you see on the calculator. What I'm going to do in this video lesson is simply talk you through the guide that I've created with this title, How to Draw More Detailed Graphs of Polynomials. There are two steps to this. The first is what's done at the x-intercepts. Now, like we've talked before, your drawing that you should have been making up until now will go through the x-axis when the exponent on a factor is odd. So here are those factors. That's one factor, that's a second factor, that's a third factor. And the exponents on each of these is 1, and 1 is an odd number. So the intercept here is going to be -1, there it's going to be +1, there it's going to be +2. And at each of those intercepts, your graph should go right through. So it does go right through at -1, at +1, and at +2, rather than bounce off. And speaking of bounce off, when the exponent on a factor is even, it does bounce off. So it should go through at -1, but bounce at +1 and go through at +2. And that's exactly what happens. Through at -1, bounces right here at +1, and goes through at -2. We've talked about this, and this is, in fact, what we've had to do on the most recent exam. Now, adding detail, how to make this a little bit more like what you would see in your graphing calculator. When the exponent on one of those factors is more than 2, 3 in other words, or 4 or 5 or so on, your graph is going to flatten out a little. And the larger the exponent, as this says, the wider that flattening will be. But even when you make that wider flattened area, don't make it any wider than the width of one space to the left and one space to the right. I'll show you what I mean behind here in just a second. As I say here, in the drawing on the right, I'm comparing x to the 12th versus x to the 2nd. In both cases, that's a bouncing situation, right? Because both of those are even. But this is smaller, that's larger, so there should be more flattening for the x to the 12th. And that's exactly what you see. If you do this on your graphing calculator, if you simply put in x to the 12th and really zoom the window in, you'll see that x to the 12th is a nice wide expanse, whereas x to the 2nd just more closely hits only right around 0. The same would hold true if those factors had been odd. So, and I apologize for the typo that appears on the guide you found on my website, but here I'm correcting this and calling this x cubed versus x to the 11th. And the same is happening. X to the 3rd, being the smaller exponent, has less flattening. X to the 11th, being the larger exponent, has more flattening here. But notice, in both cases, it doesn't flatten out to any wider than one space to the left and one space to the right of where you would expect it to go through the x-axis. So that's what you ought to be drawing. And so if you compared these two functions, this one right here versus this one right here, they have a lot of similarities. Both functions have a positive lead coefficient, both have an odd degree. The degree on this one is 1, 2, 3. The degree on this one is 1 plus 3, or 4, plus another one, 5. So 5 for the degree here, 3 for the degree there. They also have the exact same intercepts, -1, +1, and 2. In both cases, -1, +1, and 2. But in the first function, the exponent on x minus 1 is 1, and this is the obvious difference written out as a function. Here it's x minus 1 to the 3rd. Look at what happens in the graph. As you might expect, right here at that intercept at +1, you get more flattening out. And that's what I'm talking about you would do in order to make your graph a little more detailed than what we've been making up until now. Up until now, I would imagine, and on the exam, I would imagine whether I gave you that or whether I gave you that as your question, you probably would have given me a drawing a lot like that. Now that you know that this cubed number here should create more flattening, you would basically trace the same path, but then kind of flatten out here when you go around the intercept of 1, and then still drop down and come back up through positive 2. So that's it. There is one other issue, though. What happens between those x-intercepts, those peaks and those valleys? Well, in this example that I've got on the right, the x-intercepts are negative 1, 1, and 2. And to decide the heights of those peaks and valleys, just plug in a value for x. So between the intercepts at negative 1 and 0, plug in 0. And literally plug in 0 in place of x. So now I've got 1 times negative 1 times negative 2, which turns out to be 2. And so you'll find that y is 2 when x is 0. And similarly, if you wanted to know the depth between your intercept at 1 and your intercept at 2, plug in the halfway point, plug in 1.5. And here, 1.5 plus 1 becomes 2.5, and so on down the line here. And if you multiply these out, you're going to find you end up with y is equal to negative 0.625. Well, if you look at the graph, there, whoops, didn't mean to move that. There is y is negative 0.625, and there is y is 2, exactly as we had said. When x is 0, y is 2. When x is 1.5, y is negative 0.625. Now, as I say here, you'll notice, though, that the picture that the graphing calculator created is even more precise still than what you were able to do by hand. The fact of the matter is you're not going to know how to calculate the actual maximum here and the actual minimum, but the calculator has figured out that the actual maximum isn't at x is 0. It's at a different spot. So this is peaking actually and then coming back down to this point. Similarly here, this is continuing downward after you've gone past 1.5 and then comes back asymmetrically, not symmetrically here. Well, that's just something that, unfortunately, in order to get a truly precise graph, you're going to have to spend some more time studying this in math. You're going to have to take calculus to understand where to precisely put maximums and minimums. Or you can use a graphing calculator, as we've been talking about, or if you really want to, you can plot all of the dozens of possible points for all of the different x values that you can imagine. Figure out what all those y values would be, and then you can trace them by hand. My suggestion, and certainly for the purposes of Algebra 2 this is adequate, is that you follow the steps that I've taught you so far for the quiz that you've most recently had, and just add these 2 additional elements from this guide. One being, what do I do to decide how much flattening to create around intercepts, and also, what do I do to calculate the heights of the peaks and valleys between those intercepts? That's it for this video lesson.